So hello again, everyone. So this time I'm back for the R tutorial. So for this tutorial, the topic this time will be the permafrost and its evolution over time. So the permafrost is located in the very high latitudes, like in Alaska or Siberia. It's a layer of soil that has remained permanently frozen for the last thousands of years. And because of global warming, it is starting to thaw, to melt, if you like, sometimes during the year, especially in summer. And well, this frozen soil contains organic matter and methane, which are then liberated in the atmosphere. And of course, methane is also a greenhouse gas, which has which is 25 times stronger than CO2, even if it doesn't last as long in its atmosphere. So, of course, the thawing of the permafrost has very strong impacts on the methane concentrations in those areas, and of course also on global warming. And this is why being able to monitor this phenomenon of thawing of the permafrost is essential to be able to better understand and anticipate the magnitude of global warming. So in this area, we'll try to look at in this notebook, we'll try to look at the evolution of, the methane concentration, but also the temperatures in Alaska over time, over the last 20 years. So we'll try to look at seasonal variation, trends, using variables such as the temperature at 2 meters over the surface and also at soil temperature at different depth levels. And of course, we'll use some methane concentration data to enhance this analysis. So this time we are working with R. So here are the few libraries that are required to execute this notebook. So as with the Jupyter notebook in Python, we also have a pre-installed R kernel in this notebook. So if you're using this notebook on your WEkEO Jupyter Hub page, you can just load this R kernel and launch the notebook. So here's a quick overview of the libraries. So we're also using a library to process NetCDF files. As I've said, it's a standard format for scientific data. So the date will be used to easily process the date, time, and time series that we're going to compute in this notebook. So this is for manipulating data tables, and ggplot and all those other libraries will be also used to draw and generate the different graphs and maps generated during this training. So just like with Python, in R here with this cell, we import and load all the necessary libraries. So it is done here. And of course, if some libraries are not available, you can use the install packages function to make them available in your notebook. Then we'll give you a quick overview of the two products that we're going to use. So we're going to use two reanalysis products. So I'm going to start with the second one because this is the data that we're going to use earlier. So this is a reanalysis from the ERA5 platform. So reanalysis is a combination of model data and observations. So you can visit the dedicated page either on the WEkEO platform or on the climate data store, which will give you plenty of information on the resolution and on the different variables. In our case, we'll be using only the temperature variables, so the temperature at 2 meters over the surface, the skin temperature, which is the temperature of the surface layer of the soil, of the ground, and the soil temperature at several levels. So the different levels are detailed later in this notebook, but also in the ERA5 dedicated page. Here you can see that we have 4 levels, and each of them are are defined here. So different from 0 to 7 centimeters under the ground, 7 to 28, 28 to 100, and 100 to 289. So we'll be retrieving this over the last 20 or so years, so from 2000 to 2023. And we also be retrieving some methane concentration data. So this time from the Copernicus Atmospheric Service, which is which is also analysis of atmospheric composition. And this time we will be retrieving the methane concentration. So to retrieve the data, this time there is no API designed for R, for the Harmonized Data Access tool. So to retrieve the data, what you have to do is to use the traditional method. So go to the data viewer, fill out the form here for the product that we want to download, and request data, and download it in the job tab. In our case, it's all pre-downloaded. So the 3 files are available here. So the air 5 temperature, the soil temperature data, and the atmospheric composition, so the methane concentration data. So in those cells, we do some quick exploration and visualization of the temperature product. So you use the NC open function to open the data file. And here, if you want to look at some information on the dataset that you've just downloaded, well, you can do the var or the dim method to display here the names of the variables. So we have here the skin temperature or the temperature at 2 meters. Here we can display the dimensions. So we have the time dimension, the latitude, the longitude. So this is perfectly consistent with what we could expect. And you can store all those different variables, all those different, dimension and variables of the dataset in R variables using this cell. And you can even print the shapes of your new variables. So here, for example, is a sample of the surface temperature here. Here's the shape of the dataset. So we can see that it has 3 different dimensions because we have time, latitude, and longitude. So this is perfectly consistent. Now we just take a closer look at the time variable. So if we look at a sample of the time variable, we can see that it's quite a strange value that it displayed. So if you want to know more about the variable, because you want to know why time is expressed like this, you can use ncatget, this function, the ncatget function, to display the metadata of the variable time. And so we can see that we have a unit here that is expressed as seconds since 1970, 1st of January, which is actually quite a standard expression of time in scientific data also. So usually those conversions are built in Python or R functions. And so we convert the time to actual datetime values here. And now our time data is converted to human readable time values. Okay, so now we're just going to visualize the skin temperature, doing a basic plot just to visualize our data. So to do this, we reshape the data into a data frame, storing the longitude, latitude, and skin temperature. So we do this at a random day. Here is we're only plotting at a random day, which will be the first time step that we have available in the data, which is why you use index time equal to 1. Here's a sample of the data frame that we have built. So we have the temperature, longitude, and latitudes. And with this cell, we just set up a map plot. And here is the result. So we have the skin temperature on the 1st of January in 2000. So this is indeed our first date. And here's the temperature. So we can see that, as we can expect, well, the temperature of the surface layer of the soil is quite warmer in the southern latitudes than in the northern latitudes. So everything looks normal. So now let's look at some seasonal variability of skin temperature. So this time we will plot the same map, but averaging the temperature over time, only focusing on a particular month. So to look at our seasonal data here, first we retrieve the month values of each dataset, of each, yes, data point. So here for our first data, of course, we are beginning of 2000 January, so month is month number 1. And then we will group by this dataset by this new month column and to perform the mean on each month number. So this is what we do here using the group by function. And now we can easily plot so that our maps choosing one specific month. So here we choose January, April, July, and October. So it takes some time to draw all those maps, but here they are. So here we have our skin temperature in January. You can see that in the northern latitude, we can hit even less than minus 30 degrees Celsius here in the northern latitudes. In April, this is still also quite close to 0. At least most of the map is below 0 degrees Celsius. Here we hit in summer, so in July, we hit temperatures almost 20 degrees Celsius. And in October, we are back to freezing temperatures. So we can see, except maybe in those very southern latitudes here, where we are over 0 degrees, it seems. But we can see that we have a strong seasonal variability with temperature delta in some areas that can exceed 40 degrees. So in northern latitude, we go from minus 30 or even less to almost 20. So this is quite noticeable. But we can see that for most of the year also, the whole area remains below freezing temperatures. Now we're going to look at the evolution over time, but at a single point of the soil temperature. So for our sample, we are choosing a random point here in the north of Alaska. And we will try to look at the time series going from 2000 to 2023. So you can see here that we retrieve the soil temperatures at the several levels that we have available. Level 1, 2, 3, 4. And also the surface temperature at 2 meters. We retrieve the closest coordinates available to what we had defined, so our northern points in Alaska. And finally, we compute all of this in a data frame, just like as usual, and we plot our time series side by side here. So you can see that each of the curve goes from 2000 to 2023 and is colored according to the level of the depth level of the soil. And so what we can observe here is that the deeper levels, so in black here, have a smaller variability than the upper levels. And also that there is a delay between the different depth layers here. You can see here that the maximum of temperatures of the closest layer to the surface happens earlier than the lower level. So this is actually because the atmospheric temperatures have a great influence on the upper soil layers than on the lower soil layers. So now we'll try to look at the evolution over time of the soil temperature at a specific month. So to do this, we are going to subset the dataset to keep only one month value. So in this example, we're using month number 5, so it will be May. And so we have our subset dataset with still the dates and the different temperature at for each soil level. And this time, so we have this time, yes, yearly values of soil temperature of the soil temperatures at each level. And we can see that for all of those levels, we can see some gradual increase here in temperature over the 20 last years for the month of May at least. And so this increase in May also means that well, the soil starts thawing earlier than in previous decades here. And if we do the same analysis this time on month number 10, so in October, our result here is also a gradual increase here. So perhaps at a smaller rate, but still an increase. And as it is in October, it shows that well, the soil start to refreeze later than in previous decades. So basically, those two plots shows that the soil and the permafrost become more fragile with time. And so finally, we're just going to compare those temperature levels to, well, the methane concentration levels. So same as before, we're going to use NC-open to open the atmospheric composition dataset and store the variables in R variables here. And same as before, we're going to use the same random point that we had chosen before. So looking at the closest coordinate possible within our dataset. And now we're going to merge the methane dataset and the temperature dataset using the join. Well, this time we're joining on the left dataset, but there are several join functions available in R. So using the left join function, here we're just merging over the time coordinate the temperatures and the methane concentration. And finally, to be able to do a proper comparison, we will just going to normalize all those values to be able to plot them side by side, even if they represent different physical variables. So this is what we do here. You can see our normalized value now, and we can plot them side by side here. So this is the surface temperature at 2 meters, and in blue, this is the methane concentration. And we can see that both are increasing over the years in this area. So this is quite noticeable. And now what we're going to finally do is a linear regression to determine the trends followed by those two variables. So this is what we do here. Just going to quickly go over the function that we are using. So you can see here, sorry, I'm having display issues, it seems. Yep. So yes, we are using the geolam function to plot our different trends, and this is our result here. Sorry, I'm confused about the display problems that I've just had. Yes. So here are our trends plotted for temperature and the methane concentration. So we can see that we have quite a steady increase for both variables. However, there is still a discrepancy that is quite noticeable between those trends. So, which may show that the rise in methane concentration is not solely due to the increase in temperature and the thawing permafrost. So it is probable that more other complex processes are also involved in this phenomenon. So I think I'm reaching the end of this presentation right on time. So I think you have some new tools in R to compute and analyze scientific data. So if you have any question, feel free to ask. Thank you very much for your attention.
Thanks again, Alexandre, for the tutorial presentation. Yeah, it was really interesting to see something about the permafrost, and we have a few questions for you. Well, more open question about what to do also on the tutorial. The first one being, can we check for the impact on life around the area, like for microorganisms, etc.?
Probably, I don't think that there is much biological data available on WEkEO. I think we mostly have model or remote sensing products. So I don't know, to evaluate the impact, you probably have to retrieve some biological data from other platforms that cover the same time periods. I wouldn't know where, though. I'm not quite used to process like biological data set like this ones. I'm not exactly sure why you could retrieve them, but that's I would look in that direction, like, at least.
Okay, yeah, thanks. Up. Um, could it be possible to determine what's the rate to which the permafrost is melting? I think it's already been done by researcher at least.
Yes, I'm not too sure what variable you would actually look for when trying to evaluate the melting. Perhaps looking at surface areas that are concerned by the melting. And yeah, you would compute that every year and then derive a trend from that, and you would have, I don't know, a square meter per year trend in the rate of melting, but or perhaps cubic meters maybe.
Yeah, maybe. I guess well, a map with the size should be useful,
Mm.
but yeah, I think that's the main idea. Okay, so we have skeleton check. So this question, just to know, what do you mean by normalize the value? Math
Um,
class.
so basically, we have temperatures expressed in degrees Celsius or kelvins, and well, methane concentration expressed is probably in I don't remember exactly, but probably in sorry, in grams per unity of volume or mass of air. I'm doing that because I want to be able to visualize the two trends here side by side on the same plot. But if I don't normalize them, both of them have very different numerical values, and plotting them on the same plot would not be very readable. So I think the operation is done a little bit in the cell before. Yes, it's done here. Basically, you subtract the maximum and minimum of well, you normalize the your current values using the minimum and maximum of your data set to have something that is to have for each data set values going from 0 to 1, and this is what we call normalizing.
Thanks. Thanks for the math explanation also. So two more questions about R. Do you know if R or part of this software is licensed? So R is free, if I'm not mistaken.
Yes.
Yeah. So yeah, you can use R like Python or QGIS. It's totally free to use. And yeah, so the usual question also concerning the R tutorial, why use R here? Why not Python?
Oh well, well, the aim of this training was to show different tools that are useful to process data. So this was the R part of the training session, I guess. Uh, well, those two languages are very similar uses. R is also very commonly used to process such data, and also in any area where you have to do statistical computing. So it's useful to have some R knowledge
Mm.
to be able to process data. So this is why
Yeah.
we do this R training as well as Python.
Yeah, but yeah, you can definitely do the same analysis with
Yes,
Python.
of course.
It's just to show several tools to participants. Okay, I have just one last question. So I don't think you use AI in your study, but this question about
No, I
yeah,
didn't.
how can AI assist us in improving how we manipulate this data set? So it's a more open question. Um, Personally, I don't use AI for anything, but yeah, I don't know if you think it could help in using manipulating the data sets.
I don't know. I mean, it depends on what you mean by using AI. If it's just to have help for coding, it's well, just to, it can assist you in performing some more complex manipulations, maybe. If it's how we can use it to actually enhance the analysis and go further, I mean, there are already some machine learning techniques that can probably help trying to predict future or future evolutions of in our case maybe temperatures or methane concentration. Those tools can be used, but yeah, I don't use much AI myself, so
Mm.
I can't tell much more for that.
But yeah, I think just to help complete the codes or do it a bit quicker, it could be useful. But yeah, otherwise, I'm not sure either. So yeah, that was the last question. Again, a lot of kudos in the chat, so thanks again.